Hello and welcome to lecture number 3 of Momentum and Impulse in Physics 1101. And in this lecture we're going to look at really why momentum is such a useful idea, because we're going to look at what are called isolated collisions. Let's start this lecture off by looking at a very practical sort of situation. Let's think about a car crash. So we've got car A and car B smashing into each other. Here are their masses. Their velocities just before the collision are here, and there are their speeds just before the collision. And I've drawn their free body diagrams here. These are actually pretty much identical to what some of you drew in class when we were talking about Newton's third law. And so hopefully you realize that we have an action-reaction pair here. FB on A is the same as FA on B. And let's now talk a little bit about simplifying this. We've got a whole lot of forces going on here, and things could be very complicated because in particular, FB on A and FA on B are going to change during the collision very rapidly, probably. So, and possibly in very, very complicated ways. So let's see if we can do any simplification. Well, there's one simplification that's fairly trivial. Neither of these cars should be accelerating up or down during this collision to any extent. And so we know that these normals and weights will cancel each other out. And so we don't really care about them. And this is one of these simple cases where the magnitude of the normal force is just equal to the weight. And so that also tells us how to calculate these kinetic frictions. Well, let's just think about how big those kinetic frictions are, because last lecture we saw that sometimes even forces that are large, maybe we could neglect them if they're not large compared to other forces. So let's just think about the kinetic friction on A, right? In this case, N is mg. We're on a horizontal surface and nothing's accelerating up or down. So we can just say mu kn is mu k mg mag. And I'm going to say, well, rubber on concrete, right? These are both, I've said these are kinetic friction. These cars' wheels are locked. And so mu k for rubber on pavement, 0.8 is fairly typical on dry pavement. And so then we've got 1,800 kilograms times g, which is more or less 10. And that comes out to about 1.4 times 10 to the 4 newtons. Now, that's a big force. 10 to the 4 newtons, that's big. But now let's think about these forces that the cars are exerting on each other. And without calculating them, you can reason that they ought to be very big. For example, this friction force, how long would it take for either of these cars to be brought to rest by the friction forces? Well, around 2 seconds, right? These cars are not going very fast. With their tires locked, they'll accelerate at somewhat less than 10 meters per second squared. And so the time to stop just from friction would be around 2 seconds. But during the collision, they're both going to be brought nearly to rest, more or less in the blink of an eye. And so we can reason that these forces that the cars exert on each other should be very large. Now, I'm not going to go through the calculation, but it would be a good 1D kinematics problem, right? Way back in Unit 2 of the course, to show that the acceleration of these cars during the collision is something like 200 meters per second squared. I'm going to leave it as an exercise to the reader to show that. And that means that FB on A should be approximately the mass of A times that acceleration. It's pretty much the force that A is exerting on it that's doing this. And that comes out to around about 4 times 10 to the 5 newtons. So compare those, right? That friction force is a big force, but the force that B is exerting on A is more than an order of magnitude bigger. And so it would be fairly reasonable for us, if we don't need high precision, to neglect the kinetic frictions. Let's establish some terminology that we're going to be using a lot for the rest of the course. So we will often have a set of objects that we're interested in, and we'll usually define those as what we call our system. That's all we mean by our system. It's the set of objects that we're interested in. And we're dividing the world up into the system and the rest of the world, which we'll call the environment. And now, forces that are exerted by objects inside the system on each other are what we call internal forces. These are forces that are internal to the system, whereas forces that the environment exerts on the objects in the system are called external forces. They are forces that are exerted by agents which are external to our system. Let's work our way back to talking about the cars. So we have two objects, A and B, and they're colliding, and there are forces due to the environment which act on them. And we know from Newton's third law that the force that A exerts on B is in the opposite direction and equal in magnitude to the force that B exerts on A. Now the environment is also exerting forces on A and B. In the situation we were looking at, those were the frictional forces and the weight and the normal. And unfortunately, we don't have any simplifying law like Newton's third law that tells us about these forces. However, things are going to be much simpler if we can neglect the forces like by the environment, the external forces. And that's what we just argued that we could do with the two cars. This is what we call an isolated system, if that's true. If we have a set of objects where there are no forces due to the environment, no external forces, or, because that's very rare in real life, more likely negligible external forces, we call that an isolated system. When the objects that are colliding are members of an isolated system, then we say the collision is isolated. Now, very few collisions are really isolated, because there are always forces due to the environment in everyday sorts of collisions. But there's an approximation we can very often make, and we've just talked about it with the cars. For any collision which takes place in a very short time, the change in velocity of the two objects is going to take place in a very small time period. And that tells us that their accelerations are large. And those accelerations are largely going to be because of the forces that the objects exert on each other. And so the forces that the two objects that are colliding exert on each other must be very large in that case. And so we can probably neglect forces by the environment. We'll see cases where we can't do this, but we'll be able to reason through them. We call this the impulsive approximation. In other words, we say that for fast collisions, by which I mean that collisions that take very little time, the forces due to the environment can be neglected because they're much smaller than the internal forces in the system. Or, to put it another way, fast collisions are isolated, at least to a good approximation. So where does this get us with solving this collision with the car? And let's say we want to know how fast the cars are going afterwards. Well, we've certainly got simpler free body diagrams, and it seems like Newton's third law ought to be helpful, but one problem is we really know nothing about these forces, unless, you show up with the police force and you have a time machine so that you can go back in time and install force sensors on the cars just before the collision. You know nothing about these. However, there are a few things we do know. The time that car B spends colliding with car A is certainly the same delta t as the time that car A spends colliding with B. And so this is true. But we know what an f delta t is. That's a j, an impulse, right? So the impulse, I'm going to drop the vector symbols because this is a one-dimensional case, and so I'm just going to work with right as positive and not worry about vectors. So the impulse that j imparts on A is equal to the negative of the impulse that A imparts on B. Well, so what? We don't have force versus time curves, so how are we supposed to calculate these j's? Well, we know from the impulse momentum theorem that j's are equal to changes in momentum. So the impulse imparted on A is equal to the change in momentum of A. And so we have this now. That is useful because this is now an MA VFA minus VIA, right? There is the change in momentum of A, and that is equal to the change in momentum of B, which we can write this way. That seems useful because we at least know the initial velocities and we know the masses, but the problem is we still have two unknowns here. We don't know either of these final velocities. But let's suppose, as happens in many collisions between cars, oops, I've missed a negative sign here, as happens in many collisions between cars, that the cars stick together. And so we know that the final velocities of these two cars are equal. And let's just call that capital V. Now we're down to one unknown. We just have MA capital V minus VIA is negative, I keep missing that negative, capital V minus VIB. Now we have one unknown. So I'm going to take a pause to solve this. You should pause the video and work through. You're going to solve for capital V. That's what we're after here. So I've taken a moment to solve that, and here is my solution, and hopefully you've come up with an expression more or less like this. If not, then check your algebra. And I brought down the quantities that we need to deal with, and notice that we had defined right as positive, and so VB became negative 15 meters per second. And I've now just plugged those in, and note that the kilograms are on top and bottom, so they cancel, and so we get an answer in meters per second, which we had better because this is a velocity. And we find that after the collision, the two cars are stuck together and traveling to the right at about 4.1 meters per second.